Okay, so we're going to be looking at half-life and carbon dating. This is another application of exponential decay. And we have the formula for you so that we understand what all of the terms in the formula mean. We have A is the amount of the substance remaining. P, we're going to have the present or initial amount of the substance. H is considered what the half-life is. And T is the time, and it could be any measure, so years, days, minutes, or anything really. So when we deal with these types of problems, we're looking at the amount of substance or the amount of carbon-14 left after a certain number of years. And that kind of helps us date any ancient artifact that was previously organic. So we're going to just look at a mummy example. And we want to know how old is a mummy that has lost 70% of its carbon-14. And for now, we're using 5,700 years for the half-life, although it is slightly different. But for the purposes of this course, we'll keep it at 5,700. So the main thing for this type of problem is to remember that they're telling us that the mummy has lost 70% of its carbon-14. So one key fact is that you have to say, okay, losing 70% of the carbon-14 means how much is remaining? So we just have to kind of think back and say, well, at the time of death, the person that is going to be the mummy has 100% of the carbon-14. So you kind of think about it. So we started off with 100%. And if we're lost or losing 70% of the carbon-14, then we end up having 30% remaining. So kind of look into that whenever you're dealing with these types of examples. And so this is going to help us out with how to set this up. So again, we do have the formula in front of us. I'll write it out just in case. So if we have 30% remaining, we're going to keep up with using percents as decimals. So the amount remaining is 30%. We'll plug this in. Now, the present amount we're trying to think about, and actually I'll kind of, we actually don't know what the present amount is. So let me kind of even take this a little bit further. If we don't know what the present amount was, let's say the time of death, in a way, it was 100%. So that would be 1 times P, or a percentage of P. Just so that you're kind of thinking 100% of the present amount is 1P. So that would kind of leave us with the concept that when we're talking about the amount remaining, it's not just 30%, it's 30% of what we started with. So 30% of P is 0.3P. So I'm going to keep it this way for now. Now it's interesting because you don't really need to know the original amount, exactly how many grams or atoms of the carbon-14 that we have. You'll notice right away that the P's will divide out, which is kind of nice. So let me finish this off. We're taking to the 1/2. Now T is the unknown because we're asking about how old. And H, they're telling us to use 5,700 years. So we're plugging all that in. Now, remember, when you're looking at this type of equation, you're going to note that the variable is located in the exponent spot, or exponent position if you want to be a little more formal. So what we have to do first before we start playing around with these exponential equations is we're going to have to deal with what is attached to the exponential equation. So 1P. And the idea is when we're trying to usually solve for T or anything in this particular exponent position, we want to isolate the exponential expression first. So we're isolating the exponential expression. And we do that by dividing both sides by 1p. I guess you don't have to write the 1 if you don't want to, but might as well. So what ends up happening, we end up getting 1/2 taken to the t over 5,700. And 0.30p divided by 1p, you'll notice that the p's divide out because you'll never have 0 amount of carbon-14. And so this is what leaves us with our 30%. So now we're running into a very familiar exponential equation. You want to get that t out of the exponent position. The next idea would be to take the log of both sides. And whether you want to take log or ln, I'm just going to do ln. I don't know, it just seems a little bit more appropriate. So we're going to take the natural log of both sides. So that's natural log of 0.3 equals natural log of 1/2 t to the t over 5,700. And remember, the reason why you took the log of both sides, you're actually looking to release the variable from the exponent spot by using your log property. So we bring this over to the front. So that's going to leave us with t over 5,700. I'm going to write it as a formal fraction. Natural log of 1/2. And then we still have natural log of 0.3. So then your goal is to solve for t. So you could start off by saying, oh, well, I have a fraction. Maybe it's a good idea to multiply by the LCD on both sides. So if I multiply by 5,700 on both sides, what happens to the left-hand side? We end up getting 5,700, natural log of 0.3. And on the right-hand side, we'll notice that the 5,700s divide out, and we get t, natural log of 1/2. You want to take 1/2, if you want to change it to 0.5, it's fine with me. Now keep in mind, your goal is to solve for t. Natural log of 1/2 is a nice constant. So in order to solve for t, all we have to do is divide both sides by natural log of 1/2. So we will get, and I'm going to move this over to the side, we're going to get t is equal to 5,700 natural log of 0.3 all over natural log of 1/2. And remember, if we're thinking about t standing for time, we're kind of looking at, it looks like they refer to half-life as 5,700 years. So I'm assuming, with the context of the situation, that we have the number of years, so we can include the appropriate units. But you probably want to know what this number stands for. It doesn't really make sense to talk about it in terms of log form or the exact form, unless you're going to use it for something else. So this is where we'll take our TI and we'll just input it in. So we should have, let's see, at 5,700, I think we're going to have a fraction, so I'm going to enclose this in parentheses. So 5,700 times the natural log of 0.3 . So I'm closing the entire numerator. Now I'm dividing by the natural log of 1/2. Yeah, you know, you can use 0.5 if you like, but I'll just keep it exact. So I press enter, and then I get my number of years, which is quite a lot, but it makes sense when you're talking about an ancient artifact. So we have something like 9,900.703 something. So I'll show the approximation. So we have 9,700.703887. Excuse me, 9,900. 0.703887. And we're talking about years. And depending on how accurate do we want to be, you just want to make sure you're indicating that it's not a clear 9,900 years. So probably we would be okay with maybe rounding maybe to the nearest 10th or so. So 9,900.7 years. Or if there was a specific set of directions that they wanted a certain number of decimal points, then you would definitely follow those. So this is how you take care of solving these types of problems where you're trying to figure out either the half-life or how long it takes for, or how old the mummy would be if you're using a certain percentage of the carbon-14. Again, the keyword when you're starting out is the losing part. So you really have to kind of come up with the amount remaining according to the way the formula is set up. So keep that in mind. Take a little bit more time to practice these. You'll notice that sometimes they already know what the time is and they want to figure out what the half-life is. Feel free to play around. I hope this helps in the meanwhile.